Hi students, Professor Nugent here. In this video and the next, we're going to look at nonlinear functions of a single independent variable. We're going to look at two complementary approaches. One, we can generate some polynomials in X. So the population regression function can be approximated by a quadratic, cubic, or higher degree polynomial. Two, we can do log transformations using the natural log, and this is something that we've been doing in class already. Y and or x, so the dependent variable and or any of the independent variables can be transformed by taking its natural logarithm. We're always going to use the natural log. And this provides a percentage interpretation of the coefficient that makes sense in many applications, and will depend on whether you have a log of the x, a log of the y, or a log of both. We're going to focus in this video on polynomials in X. And we are focusing on a single independent variable. We can approximate the population regression function using a polynomial in X. So we can have this function yi is equal to beta naught plus beta 1 times xi plus beta 2 times xi squared all the way through beta r times xi to the power of r. This is just the linear multiple regression model, except that the regressors are powers of the independent variable x. Estimation hypothesis testing proceeds as we have learned about the multiple regression model using ordinary least squares in chapters 6 and 7. The coefficients are a bit difficult to interpret, but the regression function itself is interpretable, and so we can look at what a change in x gives us for a change in y, keeping in mind that the marginal effect will not be constant, so we expect different changes in y given the same change in x for different values of x. And we're going to show an example of that in this video. Let's think about the relationship between test score and income, where we define income as the average district income in the ith district, measured in thousands of dollars per capita. The quadratic specification will be test score of district I equal to beta naught plus beta 1 times income of district I plus beta 2 times income squared of district I plus ui. The cubic so this is the quadratic term, right? Quadratic means squared. And the cubic specification will be the same, except that it will have a cubic term. So income I to the third. Alright, folks. Let's look at the estimation of the quadratic specification in Stata. So the first thing that we need to do is generate the new variable, the quadratic term, which we can the code to do that will be generate. Then you give it you need a new variable name. We're going to write AVGINC2, that's average income squared, and that's equal to average income times average income. Then we regress test score on average income and average income squared, comma robust. So we're running regression with robust standard errors. And let's focus on the regression results with respect to average income squared. The coefficient is negative, which tells us that the relationship looks like this, which is what we saw in the plot, right? If the coefficient was positive, then we would see something like that. The p-value is 0, approximately 0. So we can test the null hypothesis of linearity against the alternative that the regression is quadratic using the null hypothesis that beta of average income squared is equal to 0 against the alternative that it's not. Right? So testing the hypothesis that this coefficient is equal to 0 is testing the null hypothesis of linearity. Because we're saying in this null hypothesis, this quadratic term does not enter the equation. And we test this hypothesis using the typical t-test. We have a p-value that's approximately 0, and so we reject this null hypothesis. We reject that thing and in favor of the alternative that the regression function is quadratic. So the quadratic term, we have evidence that the quadratic term enters the equation. Now we want to plot the predicted values so that we can see how well this quadratic estimated regression function matches the data. And you can see that the quadratic, that's this one. Let's make that nice and colorful. Quadratic. Rainbow colors. Beautiful. So that quadratic regression matches the data much better. So what you see here is the test scores diminishing marginal return to income. Right? At first you see higher increases in test score for an increase in income, and later for higher levels of income you see lower increases in test score for an increase in income. And we have the quantitative relationship estimated for this as the predicted value in test score is 607.3 plus 3.85 times income minus 0.0423 times income squared. All right, folks, we can compute the slope evaluated at various values of x. Keep in mind, because this is not a linear function, that the slope is going to change over the domain of x. So we have this same regression function from the previous slide, and we can think about the predicted change in test score for a change in income from $5,000 per capita to $6,000 per capita, and recall that income is measured in thousands of dollars per capita. So the way that we would do this is, first, it's new minus old, right? The change is basically new minus old. So we are going to calculate predicted test score at $6,000 per capita minus predicted test score at $5,000 per capita, right? So we're just going to enter in 6 and 6 into our income variables, and note that we have 6 squared here, and we'll do the same for 5 and 5 squared into our regression with the coefficients and the intercepts here, and we find that the predicted change in test score from an increase in income from $5,000 per capita to $6,000 per capita is 3.4 points. Now let's look at this effect of diminishing marginal returns. In this table, we have the predicted effects for different values of x. The change in income is the same, from 5,000 to 6,000, from 25,000 to 26,000, and from 45,000 to 46,000. The predicted change in test score from 5 to 6,000 is 3.4 points. From 25,000 to 26,000, the predicted change is 1.7 points. From 45,000 to 46,000, the predicted change is 0 points. So the effect of a change in income is greater at low than at high income levels. So you have that declining marginal benefit of an increase in school budgets. You might ask, if the change in test score is 0, moving from a level of income of 45 to 46, then what would be the effect of a change in income from 65,000 to 66,000? Does it perhaps go negative? We should proceed very carefully so as not to extrapolate outside the range of data, because then we could be making false conclusions. Okay, so we want to make predictions within the range of the data. So we would, if we are asked what the effect of a change in income from $65,000 to $66,000 were, we would have to conclude respectfully that we do not have sufficient data, because the domain of income I think goes up to like $45,000. So that range, 65 to 66, is outside the domain of our independent variable. So we wouldn't be able to make a reasonable, a rational, a defendable prediction. Let's briefly look at estimating the cubic specification. So we're bringing in the cubic term. So we have to generate another variable. So see that we're going to generate average income 3, AVGINC3, and that's average income times average income squared. And then we're going to regress test score and average income squared, and average income cubed, comma robust. Focusing on now the cubed term, we see that at alpha equals 0.05, this coefficient is statistically significant. Now, if we wanted to test the same hypothesis, that the relationship between income and test score is linear, then we would do the beta of, I'm just going to do income squared equals beta of income cubed, and that equals 0. And now we're running an f-test, right? So we would be testing the joint significance of the coefficients on the cubed and squared terms using an f-test. And if we can reject the null hypothesis, then we have evidence that the cubed and squared terms enter the equation and that the equation is not linear. And here we have that, testing the null hypothesis of linearity against the alternative that the population regression is quadratic and or cubic, that is a polynomial of degree up to 3. The null hypothesis that the population coefficients on income squared and income to the third is equal to 0. The alternative, at least one of these coefficients is non-zero. So we run this test and data. Test average income squared, average income third, and this is running this null hypothesis that they're equal to 0. The F statistic for 2 restrictions is 37.69. That p-value is approximately 0. So we reject that null hypothesis. The hypothesis that the population regression is linear is rejected at the 1% significance level against the alternative that it is a polynomial of degree up to 3. In summary, we can estimate a polynomial regression function using OLS. The individual coefficients will have complicated interpretations. To interpret the estimated regression function, you should 1. Plot the predicted values of the function of x, and 2. Compute the predicted change in y for a change in x for different values of x. Hypotheses concerning the degree of R can be tested by a t-test and f-tests on the appropriate blocks of variables. And the choice of degree R, we should plot the data to see what the curvature in the data may look like. We could also use model selection criteria, but that comes later. But once we have plotted the data, can see what it looks like, we can run the statistical test and confirm.